All right. Hello, everyone. We're just showing some slides while we wait for people to come in. So while you guys are, trickling on in, some of these slides are just going to be playing. If you want to find me on LinkedIn, if you want to subscribe to the calendar, if you want to look for a job in AI, these would be some good slides for you to take a look at. Oh, hello! Someone's already in. They've already said hello. That's all. That's awesome. During this time, it would also be great to just kind of see like where you guys are coming from. So if anyone wants to drop their location and where they're coming from, that would be good to know as well. I think we're also going live on LinkedIn. I can't see the LinkedIn people, so if you're watching on LinkedIn, it'd be great for you to say something so we can see you. Oh, okay, cool. We got someone from Seattle. Okay, Rob. Yes, I recognize you now. I see you at all these events. Really appreciate you coming out to all these. We got someone from DC. That's always fun. Okay, so we're about a minute over the hour. Most of these slides have looped once. Oh, someone's here from Palo Alto. Okay, that's fun. That's the Bay Area. So this covers East Coast, West Coast, kind of everywhere that there's tech stuff. Oh, Redmond, Washington. Okay, this is pretty much Seattle. But yes, I think this is where Microsoft is. So I bet you're a Microsoft person. If not, let me know. All right, I'm gonna shut up now, and I'm gonna bring Jason onto the stage. So, hello, Jason.
How you doing?
Welcome.
Hi, everyone. Oh, sorry.
Oh yeah, no, it's good. So we're gonna be talking about GraphRag today. Jason's from Neo4j. Jason, I'm gonna let you introduce yourself.
Sure. My name is Jason. I am a developer advocate at Neo4j. ATIC here from Washington, D.C. I went to school at American University, so always good to see folks from the Northeast. So yes, Neo4j is a graph database company. I will go deeper later into exactly what a graph database is and why you might want to use it. But in a nutshell, I work for Neo4j, and I have been a developer advocate for a couple of years now. And for those who aren't aware, developer advocates are kind of educators, community builders. And what we do a lot is go to conferences, meetups, webinars, and we give presentations on technologies tangential or directly related to the company that we represent. So in my case, I'm talking a lot about graphs or Python technologies that are kind of graph supporting. So yeah, that's me in about 20 seconds.
Okay, great. Thanks for that intro, Jason. So I'm going to pull your slides up to the stage. I'm going to pull you up to the stage here. Oh, can I remove myself from this? I don't know. But I'm going to pull your slides up to the stage. Today, Jason's going to give us a kind of a walkthrough of GraphRag. What is GraphRag and how to use it? And then I think we're also going to get a demo, right?
Yes, definitely.
Yes, awesome. Great. So that's lovely. I'm just going to hand it over to you, and I'm going to stop talking.
Cool. Thank you. All right. Hi, everyone. Okay. So as Eugene said, I'm going to be talking about GraphRag today, kind of introducing it. So the first part of knowing what GraphRag is kind of understanding a little bit of all the stuff that kind of leads up to making what GraphRag is and kind of helping define what it is. So I'm going to just really quickly talk about LLMs, RAGs, and vector stores, and then go into the GraphRag bit, and then conclude with hopefully some working demos. It's always a roll of the dice a little bit, but we'll end with that. Feel free to ask questions at any point. I think I've got the appropriate chat window on the right, so I can pause and answer questions as they come along. If I don't answer it right away, I'll get back to it at the end. Okay, so in talking about data and RAGs and vectors, I like to think of my favorite book, or one of my favorite books growing up, which is the Where's Waldo series. So if for those who have seen this book or those who haven't, each two-page spread of this children's book is filled chock with tons of people in places, and it's super interesting, right? Because you can look at every single character and they're doing something unique. They're all unique characters in this unique space. And the point of this book, or one of the points of this book, is to find Waldo. right? So I like to look at all these different people in all these different spaces as basically data, right? This is data in the wild. This is your data. And Waldo represents the piece of information that you are interested in a given moment. So if, like me, you spend about an hour staring at this one, eventually you find that Waldo is way over here in this corner. Very hard to find. He's squeezed behind a couple of folks. So, anyways, so Waldo represents the information that we are looking for. And typically, this has been a challenge to find this sort of data, right? In the past, we've had to create structured data systems to put all this data in just so we can find these sorts of insights. But the problem is like structured data only makes up like what, maybe 10, 20% of all the available data that we have. The rest of it's unstructured, right? We've recorded lots of information, but it's not in any sort of easily queryable system. This is where large language models, LLMs, has been like a real boon to sort of the data space, right? So long as the data that you're interested in has been part of that LLM's training set. So imagine this is the entire data set that an LLM was trained on. It can find you Waldo. It can find you, anything that you're kind of particularly interested in. The downside with LLMs, or one of the downsides, is that if you're trying to access information that is outside of the training set, right? That is, say, inside a walled garden, a private data set that's owned by a company or owned by yourself, this data is typically not available for a large language model to train off of. So if you ask it a question about this data, it can't give you any answers, right? So this is where retrieval augmented generation is super helpful, because what it does is it pairs an LLM with that private data so that you can make use of it and get you get this kind of combined effect, right? Okay, so let me get back here. Okay, so RAG, retrieval augmented generation, was I think proposed like a year or two ago, and the go-to database for, or go-to system for implementing RAGs has been vector databases or vector stores. Now, RAG you could pair with any database, but in particular, vectors have been very, it's been a very strong choice. And for those who aren't familiar, vectors work kind of like this. So you've got all these different characters, right? And there's different properties to each of your data points. Now, to make it useful in the vector space, what basically happens is you have an LLM create a vector embedding of the data, which is kind of like assigning a numerical value to each one of these points of data, right? So the actual number is actually quite complex, right? It's a multi-dimensional array of often float values that is only really meaningful to the LLM that had generated the embeddings. So something to be aware of when you're implementing RAG with vectors is whatever LLM you choose to create the embeddings is also the LLM you would use to create the embedding of your question. So when you're asking a question about the data, you give it to the LLM and it basically gives you a number, right? It gives you this embedding. And that embedding more or less is compared with all the data and their embeddings. So you're finding kind of the nearest number, the nearest neighbor to the embedding that represents your question. So in this case, if I'm asking a question about something, I must be asking about dogs or wolf, and we can see that this number more closely matches the wolf character versus any of the human type characters. So simplified, this is more or less what a vector store and a vector database RAG system is doing. In actuality, of course, the actual RAG vector space is quite complex, right? It's highly multidimensional. Let's see, Eugene, you're asking, are all these characters in Where's Waldo? Yes. So all these characters are in Where's Waldo, and I'll get to describing like who they are and stuff. That'll kind of play into the next bit. And what are you using to explore these vectors? Oh, okay. So this I just pulled. This is just an animated GIF of someone kind of perusing through a visualizer. I don't recall which tool they're using in this case So I'll look that up and I'll see if I can put that into my link of links later. Okay, so this is kind of what the vector space would look like to a human. It's obviously because it's very densely multidimensional. It isn't actually a 3D construct, but this gives you an idea of what the data kind of looks like and how it would be kind of clumped in those spaces. Okay, so the next step in our journey to understanding what a graph rag system is understanding knowledge graphs, which is just really another term for contextualizing data into a series of nodes and relationships. So going back to our Waldo, where's Waldo characters. Now imagine instead of everyone holding kind of a card representing a number as in a vector database, instead everyone's got threads, and the threads go from one character to another character or to an idea, an abstract category. So these threads represent the contextual relationship between one piece of data and another piece of data. So in a knowledge graph, it is filled with your kind of data entity points, in this case, our Where's Waldo characters, and those relationships, right? So when you have those relationships notated inside a knowledge graph, you get again, the contextualized information about that data that doesn't exist in like single table type data stores. So here, it's probably easier if I zoom in here. So if we're focusing on Waldo here, right? So imagine those threads that connect him to these other characters, right? So behind him was his evil twin, Odlaw, and then to his left was Wenda, which is his girlfriend, I believe. And then behind him on his right is the wizard Whitebeard. And here I've notated the relationships, right, that defined how these two characters mostly interrelate. While researching Where's Waldo, or kind of remembering Where's Waldo, this I thought was interesting was so there's actually two female characters that appeared in Where's Waldo. One is the Wenda, who you saw, and she has a sister, Wilma, and they both only appeared in like a few books. So Wilma appeared first and was, I think, originally dating Waldo, and she first appeared in what was this book? Ultimate Fun Book. And when Wenda showed up in this book, Magnificent Poster Book, this was the last Waldo's book that her sister showed up, the first one that she showed up, and it was also the book that Odlaw had shown up. So yeah, random interesting fact. But again, so this is an example of a very simple, well, the start of a knowledge graph, really. Right. All right, so let's see, Eugene, you're asking, can you do multiple types of relationships with a graph? Yes. So here I've just shown like a single relationship, but in an actual knowledge graph, on an actual graph data, you will have lots of relationships and different kinds of relationships. But you could notate like every time somebody met someone, right? So you could have every time somebody met someone, you could have a relationship created, and then basically add an additional property to that relationship, saying when that meeting had occurred.
Okay, wait. So the thing I was actually, yeah. So I didn't know that second thing either. That's very interesting as well. With these like different types of relationships, like these are like inter-character relationships, like Waldo and Odlaw and Wenda are all like characters that are related. And then you have like another color here, and like that's like a book. So like these like, and then okay, wait, what is the yellow one?
And then this one is just, I'll see if I can. So this is just where Woof the dog is from. He's from the land of Woofs. Okay. So I probably could have colored it better, but yes, you made a good point. So here I'm just coloring different type of nodes to distinguish them better. But yeah, you can have basically practically unlimited numbers and variations of node labels, right, types. And so here I've got red for characters. And the interesting thing with a property graph database like Neo4j is you can assign one node actually multiple labels, right? So this could, Woof isn't a good example, but like Waldo is a person, but if you're using a person node for, say, employees, you could notate them. Here, this is a person, this is an employee, they're also maybe a vendor, a partner. You can have multiple labels on one entity, which, is, matches up with real life, right? Like when we know an entity, oftentimes there'll be multiple relationships to that entity, and that entity is known by several different categories.
Okay. So is it also possible to like so I like it doesn't make sense in this specific scenario, but would it be possible to have like Waldo like appeared in Wizard Whitebeard or whatever, like first appeared and like point that towards Wizard Whitebeard, or is that something that we have to like think about implementing ourselves as like a safeguard, or is that something that would automatically be like, hey, you're not supposed to do that?
No, like so the data itself stored in a knowledge graph or a graph database, it's not inherently limited. These are types of things you would want to implement if you're using a graph database to represent your data, right? Because certain domain spaces you'll want like, okay, so like this chemical should never interact with that chemical. So you should notate that relationship or that restriction. Um, but the underlying data framework isn't limited in that way.
Okay. Oh, cool. Interesting. Okay. There's also another question from the audience, so I'm gonna let the audience ask.
Okay, let's see. I believe nodes can be in the form of embeddings. Given the cost implications of the GraphDB, would there be complementary DB used alongside a GraphDB for graph-based RAG? Okay, so I think what you're asking is, can you use a different system to store the embeddings, right? And then use the relationships in the graph database to kind of complement that data. If that's the case, then yes, you totally can do that, right? So you're right. Putting embeddings directly into the nodes, you can do this, and we actually recommend this for like experimentation and trying out smaller data sets. But if you're at a very large scale, you're right. This is going to be very costly, and it might also, depending on what your queries are, it may add an unnecessary kind of burden to your query to kind of go through these embeddings. So yeah, you could use another vector store, and this is something we're actively exploring with some of the vector database companies. Is how do we play well together, right? How do we have the vector embeddings inside a really high performing vector database, and then have all the interesting interrelationships, interconnected relationships in a graph database, and then marry the two and give you really solid results. So this is an active space of development. Um, but yes, there is nothing theoretically or technically that prevents you using multiple technologies together to get to get better answers, especially with large language models. Let's see, would you be sharing in this or another session some potential examples of this joint stuff? So this is, again, something I'm actively working on. I won't be showing any of those experiments in this session, but maybe, I don't know, after we've run it through the ringer a few times, maybe I'll come back and do another session with Eugen and show that off. So definitely, keep an eye on all these sessions and both our feeds when we've got these examples ready. We'll post them as soon as they're viable. Okay, if there's no more questions for now, I'll continue here. So okay, so here so the typical pattern for creating a knowledge graph inside a graph database is there are a couple ways you can do this, but kind of one of our recommended paths is to start with the questions you want to have answered. Like, what information are you most interested from your particular data set? Once you know generally what questions you want to ask, that highly informs you in deciding how to construct that data model. So um, what I showed earlier, this is an example of what the data would look like, but also kind of so I'll come back to data models, but data model is basically this, but this just to specify the schema of the data, not the actual data entities themselves. So after you've got at least a starting data model, the starting schema. You then can use that to build data import ETL processes to take data from wherever it exists currently and pull it into a graph database. So this is the typical process that has existed at the start of graph databases and prior to large language models becoming a huge thing. Now, this part here, the data model part, this was probably probably one of the more challenging parts to implement because as you saw, there are many different ways you can tie different entities together and many different ways you could represent entities. And that sort of unlimited potential can be difficult unless you're an extremely unless you know that your particular domain space intimately and are able to easily kind of parse that out and put it into this sort of napkin drawing data modeling structure. Ah, so again, this is still a viable sort of development path. But with the introduction of large language models, we're able to kind of accelerate this process. So this is kind of our first part of GraphRag, right? So the two components of GraphRag is using generative AI to help import data into a graph system. And then the second part is, of course, the retrieval part. Okay, so part one. So I'm going to show off a demo of a knowledge graph builder app that our team has been working on. And basically how it works is you take some sort of text data and you bring it in, and then you split it into smaller chunks. And then you hand those chunks to a large language model to create, in our case, it'll be two things, to create the embeddings that represent each chunk, right? And then you put that into, you got the vector embeddings that will eventually go into a data store. And in our case, we're doing this and we're also using a large language model to take that chunk of data and pull out, or to identify any entities and what relationships should exist between those entities. So we're basically parsing that text data for graph-like data. And then we're taking those graph documents and we're putting those into the graph database as well. So both the embeddings and the nodes and relationships are being generated at the same time. Okay, in a two-dimensional view of vector data, it'll look something like this, right? You'll have lots of individual nodes with the text and the embeddings, and they won't be connected if you're just going the vector route. And this is, so I'll show this app in a moment, but I'm just going to go through these screenshots because the import process takes a couple minutes, and rather than us sitting for 3 minutes for it to complete, I just took snapshots of this process. So this is the UI of this particular demo app, and we do it. The code is open source, so at the end when I show off the link of links, you can, it'll have a link to this repo. So you can check out this code for yourself. You can implement it, you can fork it and grab some ideas. You can use it as you please. And so this app, in a nutshell, it's got two main components. One is a React front end, which is the GUI that you saw, and the backend, which is running off it's a fast API Python server. And under the hood, it's using LangChain, which is a large language orchestration framework for kind of help managing all the prompts and the other technologies all together into a sensible sequence. And the main technologies that this demo app uses is OpenAI, or you could use Gemini for running the LLM portion, and then Diffbot for helping create the knowledge graph components from the text, and then of course Neo4j for storing the data. Okay, let's see. Tom asked a question here. GraphDB data schema is always hand designed. Are there automated ways to complex domains where AI infers the most relevant node and relationships definition? Example, LLMs be helpful in schema design. Okay, yes. So this is where this app is going. So yes, this is an active area of development. Various tools are starting to pop up to help take various types of data and turn it into a data model. At this stage, even with these tools, I would still, you still want to take a look at that data model that it creates after the fact. And I'll go into, I'll just continue with this, and then we can have that discussion. Okay, so here I'm just using the YouTube importer option. So this just takes a URL link of a YouTube video, and the YouTube video I'm using is the recording of Eugen's talk from, I think it was 2 weeks ago, with Changshe of LanceDB. So I just put the URL of that in, I click submit, and this took about close to the 3-minute mark that was predicted by the system here. And there is a progress bar, so once you kick off, you can you can watch. But what you'll likely do is probably pick a few different items here on the left, and just you can upload it all in a batch. Okay. All right. So after 3 minutes, this completes, and you'll know it's complete when you see the completed status. And once that's ready, you can jump into any one of our visualization tools to kind of check on the data. So here is a screenshot of the data that was generated. And what I'll do now is I'll actually go to the actual workspace here. Okay, so here on the bottom, let me make this bigger. Oop. You can see here, this central node here, this should be the document or the YouTube video. Oop. Okay, I gotta figure out why it doesn't want to give it its name. Oop. All right, yeah. Okay, so so what we're looking at here is Neo4j's browser. This is kind of the primary tool for running Cypher commands, which is the query language for querying graph data. It is one of several query languages, but it is our query language. It was open sourced, or an open source version of it came out quite a few years ago. And sorry, sidebar. And as of last month, the ISO standard for a graph query language, the GQL graph query language, which can be easily confused with GraphQL, and often is, but it is separate, right? So GraphQL is for kind of a REST API alternative, and GQL, just the acronym, represents the ISO standard for graph query languages, which looks a lot like Cypher. So if you were to start with either, you'll find switching between the two not that super cumbersome. Okay, so what I was trying to do was just notate the system to display the document as, or display the file name for a document, so that when I zoom in, I can see that here is what I pointed to, and all this data was created from the transcript from this video. Okay, so fortunately I'm a little sluggish between the screen share. Okay, so what we're looking at here, this is the data schema, right? So this isn't representing all the individual data as was represented in this view, but the data model, which was being asked about earlier, for like, this is the sort of thing that was handcrafted prior. And now you can see, with the help of an LLM, we can quickly create a pretty sensible data model here to start with. But you can see here that we probably have more relationships than you might want to, that you wouldn't have probably added this many relationships if you were handcrafting this. You probably would have simplified the number of relationships, right? So if I try to peel this out, we can see just between concept and software. Actually, let me put it on the other side, it might be easier. Oop. I want to go here. Right, we have, let's see, zoom in here, all the relationship types: resolve pain points, compact, follow, soft delete, upsert. Geez, did you guys talk about this much detail in talking about software and concepts? You did? I might have to rewatch that video. But anyways, it's easy enough to so unlike other databases like SQL databases, like adjusting the data schema is actually not as difficult in a graph database compared to those systems. Like all you really have to do is in your data is either find all those relationships of a certain type. So like here, hopefully I don't execute this, but say if I'm looking for all like so I've got effect and effects. Probably don't need both, right? So I could delete them. I want to do this. Attach delete R, which would remove all these relationships, or better probably would be to rename them. But all you have to do is as you're affecting the underlying data, this data model gets updated, right? This data model just represents all the actual relationships and entities you have in your data. So as you're updating that, this data model will update to reflect that. So you don't have to do sort of this pre-planning that you usually have to do with other databases. Unless, of course, you're adding in a lot of constraints and indexes to help speed up the queries later, then those you kind of have to turn those all off before you affect those systems and then put those back in. So just be aware of that. Okay. A couple more questions here. Okay. So Sangil is, I'm trying to understand the advantage of the GraphRag model. My product generates narration scripts for attractions, example, the Eiffel Tower. What are the biggest advantages of using GraphRag over regular RAG for this use case? Okay. So vector database is great. They're great for pulling like one specific information. So if you have, let's see, so if you've got like a description of a given attraction, right? And it's in some particular document, a PDF doc or a website. Vector database will pull that direct resource very quickly, very easily, and it does that very well. But if you have a multi-hop question, right? So say you're not looking for specifically an attraction by its description, but say you're like, okay, give me a recommendations for attractions for a person who happened to come along with another guest, right? Like, and depending on how much information you have in the graph store, but let's say you've got quite a bit of information on the guest coming in and their guests. So you couldn't ask a vector system like, give me like the top 3 whatever attractions that this person should go check out, based on the fact that you only know like tangentially like how this person is interrelated. So the Kevin Bacon, 6 degrees of Kevin Bacon, any sort of like question like that, vectors can't do these multi-hop questions unless you do a lot of work with putting in extra information, metadata, and then starting to have metadata point to other metadata. So there are these strategies that are appearing in vector RAG. But if you take a look at them in detail, they're basically pointing to the direction of eventually ending up at becoming basically a knowledge graph, right? So recommendation systems are a great example of the use of graph-based systems. Also, like kind of tangentially, like say you wanted to do a shortest path plot. So your attractions are in a given space, you have given walkways, you're wanting to know, like, okay, when a guest comes in, what is the most optimal route for someone to hit all the attractions that they're interested in, right? So not only can you give them a recommendation of what attractions they should go to, you can also give them a plot of like which attractions they should go to first and then end up at, right? So all like like Google Maps or Apple Maps, the road plotting systems, those are under the hood. They're all graph systems. There is no non-graph shortest path algorithm that I've encountered, that I've found. So that sort of problem it's particularly graphy. Okay, I hope that answers your question. We can talk about that more in a moment here. Okay, so this is the data that's that was extracted from the video. Okay, so I'll come back here. So if you're so one limitation of YouTube transcripts that I encountered while preparing this talk is that this is kind of what the transcript looks like. It is all the words that Eugene and Chang had said, but it did not actually identify who was saying what. So when I pull up this demo later asking about or asking a chatbot about the content, it won't be able to answer questions about Eugene and Chang directly because it doesn't know uh, who they are. Well, it knows a little bit about Chang because Eugene had introduced him. But anyways, so if you were to do something like this, uh, as a side note, my recommendation would be to run it through a system that is able to identify the speakers and then take this text and build a knowledge graph off of this. I did a little experimentation with this with some side tools, and this worked pretty good in terms of identifying who said what. So just this sort of small sort of data cleanup helps immensely. So basically, what I'm saying is, as with all sort of data projects, the better the better your incoming data that you're working with, the better your end results will be in general. Okay, let's see. So this I use Descript. So Descript is I think it came out primarily as a podcast app. And so what I did is I just took the audio from the YouTube video and I just dumped that into Descript. And Descript took a couple minutes to identify, just to transcribe everything. And when it first goes in, it doesn't know the people any better than YouTube does, but it just goes speaker one, speaker two, and then because I know who the speakers are, I went in there and just kind of updated like, okay, speaker one is Eugene and speaker two is Chang. And I only had to do that once, and then it was able to more or less correctly identify everyone. It's not 100%, but it's like 90%. So it's much faster than kind of manually transcribing anything. And Descript also has a defiller word tool that was also helpful. So there are a couple tools like this out there, but the one I used was Descript. Okay, now the second half of GraphRag, which is the retrieving data part. Okay, so how this works is pretty much the same as any other RAG system, right? So you have a user who asks a question, it goes into whatever system that's been set up to run GraphRag. And in our case, it's going to both create a vector embedding of the question and also do a text to cipher conversion. So what the LLM is doing is it looks at the question and it looks at the data model of the graph, the data that's in the graph, and it goes, okay, it tries to construct a cipher statement to get the answer that you're asking for from the structure of the graph. Right. So then it queries the graph database. It gets a response. It takes the answer and it more or less aggregates the responses from the vector and the from the graph. And there are a couple of different techniques you could do with this, right? You could run the graph portion first and then kind of filter post that with the vector embeddings, or the other way around. You start with the vector embeddings, you pull up a number of different resources, and then you run a retrieval query around those data points that were pulled. So you get the entities from the vector search, and then you also get a chunk of the subgraph, a part of the graph that's associated with those data points. And then you send that all back to an LLM. LLM kind of looks at it all and kind of aggregates or synthesizes a summary answer and provides that to the user. Cool. Okay, Rob mentioned, love this. One important theme is that RAG can work some magic, but if we have it work with less than desirable data, we're going to get less than desirable results. Yes, yeah, right. Talking back to, the famous adage, was it like garbage data in, garbage, I guess, insights out. Yes, the quality of the data you put into any one of these systems is going to net you far better benefits than spending a lot of time trying to do magical prompt engineering. Okay, so back to this demo app. So in the far right lower corner, there's a QA chat button. So built into this tool or this demo is right here. Let's see, make this bigger for you. Is this chatbot implementation. So if I close this, so it'll be here on the lower right, click on that. So once you've loaded up some data, you can immediately ask this chatbot questions on that data. And so ideally, you want to start with the data here. So obviously, if I ask any questions that that ask a question about data that doesn't exist in here, then it's going to give me nonsense. So here I'm just looking at the data model to get a sense of like, okay, what type of questions can I ask it? And here I can see that technologies were talked about, companies, industries, and concepts. So if I look here on the right, I can see that there are 24 nodes for software, 14 for organization, and 6 for company. Okay, so I'll ask like a company or software question just to start off with. Now I can. All right. So we had company. So, what companies were discussed? And I'm actually not expecting an answer. Weirdly, because so I tried this a lot over the last couple days, and I would say probably 1 out of 5 times it gave me the expected answer. Um, and I'm not entirely sure why this is the case with this particular demo. I don't know if it's not accessing the data correctly, or perhaps it's expecting a different type of structured data. So one of the takeaways from a lot of our experimentation, a lot of our work is if you know the data model, right? If you know the model or how your data is structured, all the downstream tooling can be tailored to this and generally works really, really well. Like this is, kind of our mainstay when someone knows their data model and builds analytical tools on top of their domain space, they get great benefit out of it. One of the challenges that we're encountering with these Gen AI experiments, because of the non-deterministic nature and the fact that you can come out with like if I rerun this app a couple times, I will get a different data model each time. So creating a general purpose graph rag system is we're like at the cutting edge of this space, right? So it's all new, and sometimes it's like, wow, it works really great, and sometimes it's kind of like, well, that was kind of not what was expected. But one of the great things about a GraphRag based system is that whatever the LLM is telling me, it would be ideal if I could get it to give me any answer. Let me ask it about. Let me try one more question here. What software was discussed? Is any question that, if it does give you an answer, is you can go into the graph data itself and verify if the answer is correct. Okay, so I'm not having luck today with this particular chatbot, but I do have another demo up and running here. And this is, okay, so let me show you the data model for this. So this demo here is using the Microsoft Northwinds dataset, which has been around for quite a long time. And the Northwinds data is basically a mock retail data set, right? So it has customers, what they bought, and how many of the thing they bought, and categories of those products. So from this data, we have this demo here, which is primarily showing the difference between a vector-only approach and a vector graph approach. So here I can ask, so what are the top selling products? So here, I would expect the answers to be more or less the same between these two. Okay, so here the graph one just gave a little more details. They are not tofu. Okay, they roughly match up. Okay, so this is a example of a good single hop question. You could ask any database this, and you get you should get the same answers. But now, if I want to ask something multi-hop like who buys or what two products are most often bought together? This one, yeah, I would not expect Vector to give me that answer, right? Unless somebody had written somewhere in the content that, oh, these two products are the best. So the two products that are most often bought together are Philo Mix and Jack's New England Clam Chowder and this other combo. And to, I guess, put a nail in the coffin. So what two products are most often bought together and who buys these products? This one is a series of hops, which I don't think I've ever seen Vector give an answer for. And I don't really expect it to. But this information does exist in the graph. And if the LLM is able to generate the right cipher statements, it should be able to answer this. Let's see, not formatted the way I'd like, but the two products most often bought together are, what's this, float mice offs? This other product, and it's bought 6 times, and the customers who bought these products, or are these all the products? Okay, so anyways, long story short is you can see that we get some sensible answers, and if I wanted to spend the time, I could go into the actual data here and run a couple queries to confirm that, which I won't do today because I want to finish out this. But just know that you can go in and you can query the graph database to confirm or deny the answer from the large language model. Okay, let me wrap this up real quick. Okay. Oh, last thing I want to mention, if you're interested in more graph information, we've got a conference at the end of the year. So you can sign up to join us. We've got 4 tracks: applications, AI, data science, and graphs. All right, Eugene. I mean, I've got a couple things I could keep talking about, but I wanted to address any questions first before while we still have time.
Yes. So I think this is the first question in chronological order that was asked, which is, are you using a model specialized in text to cipher or a generalist LLM?
So I was using that one was using a general LLM. I believe it was just using OpenAI with some prompt engineering. Now there are some fine tuning that people are doing with different models. I have yet to be told of like, oh, this fine tuned model is the best one to use for text to cipher. Use this one. So again, it's an active area of experimentation and testing.
Okay. Next one is from Alina. How does LLM receive data from the graph?
Okay. So it's just like doing a query to any other database, right? So it runs that cipher command, and the answer it gets back is a JSON payload. So it'll have one of several types of answers, right? It'll either have just like a message like count of something, 6. The LLM is smart enough to go like, oh, okay, so 6 is the answer to that person's question. It'll just pass that number to the user. If the payload is a little more complex, again, the LLMs have been generally pretty good at summarizing, the data it gets back from its own cipher queries. But basically, that's what's happening, right? Is the LLM is not interfacing with the data directly. It is creating a query. The query runs through, normal interaction process, gets a payload back, and it's only interacting with it's creating the query and interacting with the return data. So that's how it's interfacing with the graph data.
Cool. That makes sense. Kartik asks, are there any starter references for personalized user recommendations using GraphRag?
Ooh, okay. So my go-to for that specific question, I don't think I have a good reference off the top of my head, but in general, I recommend everyone check out our Graph Academy section. So these are all free online courses that our team maintains. And here, you probably, if you're a Python developer or even your TypeScript, so I would recommend looking at one of these two courses here, right? Build a Neo4j backed chatbot. And this at least covers all the basics of implementing a GraphRag system. And then what you'd want to do is take a look at one of our articles or one of the community's articles on creating recommendation systems. And then you kind of want to marry the two, right? So you just kind of want to make sure the GraphRag system is asking recommendation targeted queries or graph algorithms to run.
Yeah, I think that makes a lot of sense. These are great resources to check out, guys. So Jay asks, thinking about social media applications, would you create one huge graph database with certain restrictions or rights, like maybe like RBAC type thing? Or would you create separate graph databases for every individual and then join them?
Okay. So a couple different ways you could do that. I mean, if you're just starting off, I would say one big graph database and then use so the enterprise edition includes RBAC, so, and multi-tenancy. So that would probably be the best place to start. If you were to, get up to massive scale, then you'll want to do like multiple database instances or clusters and kind of peel that off. Probably starting with regions might make sense. I wouldn't spin up a database for each individual unless this was a very particularly unique social network where it has very few people, but the information density is super high. Then that would make a good use case for having separate databases. But yeah, I would start off with like a large enterprise edition, a large enterprise instance that can take a lot of nodes, a lot of relationships, and has RBAC built in.
Yeah, I wouldn't do that for every individual user either. I think there's a lot of overhead that goes into that just is unnecessary.
Yeah, because you'd have to keep coordinating all the data and make sure you don't have like, yeah, you're right. There's a lot of extra work in there.
Okay, so Tom asks, what underlying constraints of today's LLMs are most significant to production effectiveness with GraphRag? And which constraints do you see improving fastest versus maybe not improving?
So, I mean, I guess the elephant in the room is really the cost of running LLMs, right? So even if you're creating like synthetic data, right? Like to do it through normal means of generating mock data, all runs very, very fast. But once you add an LLM to the picture, like, I mean, imagine asking an LLM, like, generate me 10,000 fake employee records. That's going to take a while and it'll burn through quite a few tokens when you could do the same thing through functional programming and have it done, within a few seconds and cost you next to nothing. So I think that's probably one of the biggest factors with implementing LLMs in production at all right now is the cost to implement, right? Like for a given use case, does it make sense to run an LLM every single time you want to do whatever X, right? When just running maybe a query or running another system is going to be way more cost effective.
Makes sense. William asks, would GraphRag be good for using LLMs to write a book and organizing based on lessons to teach for a self-help book?
Oh, yeah, that's a fun use case. Yeah, I would think so, right? Because I mean, like the learning paths that you have would make for a good small graph, right? Like which type of routes you can go, and you can also store people's sort of progress through. So actually, I think it was in this lesson, this building a Neo4j backed chatbot using Python. So Adam Cowley, who runs most of Graph Academy, so he added very early on, he added a chatbot to the course. And as the data set that he's working with is not only the course data, but the people coming in and which courses they're signing up for, which ones they're interested in, how far they're getting along. So actually that's a very close mapping to your particular use case. So yeah, take a look at that course. If you want, reach out to me too, and I'll connect you with Adam because Adam, I think, will have a lot of good insights for what you're tackling here. But yes, in general, the short answer is yes. I think it's a very good use case.
Cool. I think we're through with all the questions, and we're also wrapping up on time here. So I think we'll call this a day. So thank you for giving us such a great presentation, Jason. Thank you guys for coming, and I'll see you guys, I think, next week. So peace.
Cool. Thank you. Thank you.